So hello everyone, my name is Yusra Afer. I'm from Purdue University, and today I'm presenting my work on Android precise protection mapping, derivation, and reasoning. So this work has been done with collaboration with my lab mates and under supervision with Professor Zhang and Li. So first, Android map provide a specification that maps each API to a set of permissions that states what are the needed permission to execute an API. So basically, we have here an example. To invoke the API at GPS status listener, an app needs to hold the permission access find location. So developers rely on this permission to understand these mappings to understand what is the permission required to for the execution of their app. So it's a very valuable input for that. And it also has been used by the research community to address various security problems such as component hijacking and overprivilege. So if there is an imprecise maps could definitely lead to a lot of problems. First of all, developers want to understand what is the correct sets of permission that are needed to execute their apps. And then they could ask more permissions than what's needed and lead to overprivileges. And also it could lead to false positives in detecting component hijacking. So the research community has three main works that try to build protection to API mappings. First, an early work called Stowaway uses feedback directed API fuzzing and dynamically logs permission checks to during API execution. So these checks will be the extracted permission will be very precise for that execution. But if any path is not covered, then they will miss those permissions. To overcome the limitation of coverage, P-Scouts relies on static analysis to extract the permissions statically. So it reports all the reachable permissions from an API. And recently the work A-Explorer conducts a more precise and accurate analysis of Android framework based on their understanding of some challenges that characterize the Android framework. So up to date, that's the most accurate mapping. But we see that the static analysis work reports the permission maps as a set. So basically, if two permissions are detected, then they report it as there is an end relationship between them. But in real practice, these permissions might not be all required. So a different path might require different permissions. These limitations are mainly due to the fact that they don't consider path sensitivity. So to illustrate and justify why path sensitivity is important, let us look at the following example. So here we have two apps. Here we have two users. Just for background information, Android allows users to share the same phone. Each user will have his own setting. So here we have two apps, two users, user Alice and Bob. Alice has two apps installed, the blue app and the green app. And Bob has one app installed, red app. So each app has a set of inner components. Assume, for example, the blue app has a search component and it has also another component like explore. So now the green app in Alice environment needs to disable one inner component. For this purpose, Android provides one API called setComponentEnableSetting. It takes as an argument a component name, for example, search / a green app / search, and also takes a user ID to which this app belongs. Is it Alice or Bob? Denoted by user 0 and user 1. If green app wants to disable its component, it can call the API as follows. Once invoked, the search component will be disabled. So clearly, this API needs to enforce some access control. Otherwise, any app can disable components that belong to other apps, or users can disable components that belong to other users. So for this purpose, Android enforces a layer of access control checks. So let us look how it's enforced. First, the supplied user ID is compared to the current user ID. So basically, we're checking if the calling user is updating her own components. If not, then the caller, the system checks if the calling app is system, Otherwise, it checks if the caller holds the permission interact across users. If this one fails, then the API will fire a security exception and stop the execution. If any of these three checks holds, then the API enforces whether the calling app is updating her own components and not a component that belong to other apps. If not, then the system enforces another permission called change enabled setting. So we see that there is a lot of checks here, and saying just that it's a set of permissions that are needed to execute this API is actually imprecise. So let's see how Explorer states the map. For this API, it states that there are two permissions needed: component enable state and interact across users, which is imprecise as stated. This limitation is due to the fact that the path sensitivity is not considered, and also some additional dimensions like the UID or user ID are not considered as well. To address this limitation, we propose to derive precise protection specification for Android APIs. And our solution, which we call Arcade, construct the map in a path-sensitive manner, and it also considered additional control dimensions. Please note that we call it protection map and not a permission map because it also contains additional access control dimensions. We derive the map based on a novel graph abstraction technique that we'll discuss later. And we propose a logical reasoning-based solution to detect overprivileged apps and component hijacking. So now we'll show how our protection map looks like. So here we have 3 disjoint checks that correspond to the first part of the code. In addition to that, we have 2 disjoint paths for the second part of the code. So our map is actually complicated compared to the existing works. So our solution has 2 modules. The first one generates the protection map, and the second one leverages this protection map for the detection of component hijacking and overprivilege. So here we use the same API that we discussed in the motivation example to show how we construct the maps. Please note that this code now contains more implementation details, because we want to show how we process the code to extract the protections. So starting from the entry point, we analyze the CFG to identify access control tags. The CFG construction is as follows. First, the code checks if the user manager exists. If it does not, it simply returns. Otherwise, the code checks if the class name of the first parameter is null. If so, then it sets a local variable to be true. Otherwise, or in all cases, it gets the binder calling UID. And then it compares the calling user based on this binder calling UID to that of the supplied user ID. And then if it doesn't hold, then it compares if the UID is equal to system, and so forth, as we have discussed in the motivation example. So this CFG, even for this very small piece of code, is actually quite complex. This is because, and besides, the nodes in the CFG are actually not all of interest for the construction of the protection map. They are not related to access control, all of them. For example, the yellow node 4, 5, and 6, they don't abstract any access control. They're just for input validation or for the internal functionality of the API. So to precisely capture the access control logic, we introduced the concept of access control flow graph, which contains only the instructions and control structures that are needed for building the protection maps. So let's see how we construct the AFG. First, we start by initiating the AFG with 2 special nodes, exception and granted. So exception means that the program has stopped, there is either an error or a security exception. And for granted, that means that we have reached the actual functionality of the API. For example, when we call bind or clear calling identity. Then we add all the security nodes to this AFG. For example, node 9, which is a system check, we check the UID against that of the system. And then node 10 or 11, they enforce permissions. Then we add to this graph all the access control, all the nodes on which access control depends on. Like node 12, which gets the packages setting. And then we also have a case, which is node 4. This node 4 checks if the user manager, if the user ID exists. But this one actually does not, is actually a case of input validation, even though an access control check depends on it. So for this specific purpose, we just remove it. And then the next step, we just connect the graph nodes with the edges while preserving the actual control flow inside the CFG. And for the node 1 and 7, we see that we have removed node 3, 4, 5, and 6. So we just connect them using one single edge. And then last, for any predicate to which we only had one path, we add another path to the granted node, like node 13 and 14. So now we have this AFG that we have constructed. It abstracts the access control path very accurately and precisely, and it's less complicated than the original CFG. So to extract the mapping, the process is straightforward now. We basically traverse the graph and extract path conditions of all the paths from the entry point to the granted node. And then each path will denote a way to acquire the needed access. And then our protection map will be in the form of a first-order logic formula formed by the disjunction of the path conditions. Here we have the map for this specific API. We have actually 6 paths here, but for illustration purpose, we only report 2 paths here. So the first path here corresponds to the path in the AFG, this one. So this map could be actually very complicated and contains a lot of negations or terms and clauses. So we also simplify the logic formula using known algorithms such as a Quine-McCluskey algorithm. Then developers can understand this formula much more easier. In the second part of our work, we leverage the map to identify traditional security problems like permission overprivilege and hijacking. If we leverage existing work, the application is very straightforward because we just need to compare the set of requested permission against that of the set of needed permissions. But in our work, that's not very straightforward because we need to identify the weakest protection path to invoke the API. And for this purpose, we translate the problem into a logic inference problem. Let us look back at the example that we have discussed earlier, where we had 2 users and they had apps installed. And now assume that the green app wants to disable a component that belongs to the green app. And the call site is as follows. First, we have the component name is specified by blue app/search, and the user ID is specified by user 0. So the app is disabling component that belongs to the same user, but to a different app. But if you use a Explorer, it states that to invoke this API and this context, we need 2 permissions: change component enable state and to interact across users. But if we use our map, we see that the first check actually holds because the calling user ID matches that of the specified argument. So we can bypass the permission check that's required in the first part of the map. As a result, only change component enable state is required. So we see that if we use other approaches, we have overprivilege detection, but it's actually false positive. We only need change component enable state in this case. So more formally, to detect component overprivilege, given context C of an API at the call site, and for example here, the calling app's name and the user ID, and the protection map of the API, we query constraint solver for the solution of variable permission, denoting the needed permission in order to satisfy C and M. More details can be discussed, can be further. We can see more details in the paper for this process. Now we move to evaluating our protection map. We rely on three analysis. First of all, we compare it against Explorer, like against their protection map generated. And the second part, we evaluated using by applying overprivilege and component hijacking. So first, we have collected 8 different images from AOSP as well as from 4 different vendors. For ASP, we first extracted all the protected APIs. There is at least one permission or UID check that occur inside these APIs. And then we extracted the ones that need one single path of protections or the ones that have multiple paths of protections. So here, this column reports the number of APIs which had one single path. So this result should be the same as that of Explorer. These columns here reports the number of cases where we had at least one UID or user ID check. So we see that there are 28% of APIs which apply this additional control dimensions. If we don't rely on this UID and user ID checks in the construction of the protection maps, we will have 28% of APIs that have inaccurate mappings. And the last column reports the number of APIs which had at least two paths. Basically, they have multiple paths. So we see here that 41% of APIs enforce conditional access control checks. So for these ones, if we rely on Explorer map, we see they will have imprecise mappings. We further perform another experiment on the customized images to see if they have any differences in terms of detecting the component, detecting absolute or conditional enforcement. And there is 51 of APIs which enforce conditional access control checks in Samsung. The next experiment, we state that the cases of APIs which has disjoint path, and we ranked them based on the frequency. So for the first category, denotes the user checks. There is one permission and one check that checks the calling user or the supplied user ID. These have been added to Android framework to implement the multi-user access control checks. And the second category reports UID checks. So there is the caller actually is privileged enough to bypass permission check. For example, the APIs check the root if the calling UID is root or system. In the last category, we see that we have disjoint permission checks. For example, a lot of APIs require either find location or course location. Almost never the two permissions are enforced at the same time. So only one of them is actually required. And now to detect overprivilege, we have collected around 20K application from different vendors and applied our analysis to detect overprivilege. So we found that 61% of apps are overprivileged, and Oppo has the highest overprivileges, and HTC has the lowest. Then we further performed the same analysis by relying on a Explorer's map. The number of reported and needed permissions for a Explorer is actually lower than us, because they don't perform path sensitivity. On average, we detect that 2.5 permission are actually unneeded, which is an increase of 43% of the other approach. So this clearly justifies the need for path sensitivity. And then in the second experiment, we performed similar things on component hijacking. So we found that the number of hijacking cases ranges from 1.3% in Sony to 4.6% on Oppo. On average, we can detect less vulnerable cases. Please note that the other vulnerable cases that can be detected by Explorer are actually false positives. And we also performed another experiment to extract the number of components per app rather than the number of apps. And we see that Explorer can detect 11.8 more components that are overprivileges, that are possible hijacking cases, but they actually also false positives. So to conclude, we propose Arcade, which is a novel approach to derive precise specification for Android APIs. We have leveraged this mapping to detect hijacking and overprivileges. And our evaluation shows that path sensitivity analysis is important. Thank you.
Questions?
Will and NC State. Really cool work, and I think it's a really valuable that you've taken this from the and down to the logic. And I saw that you've uploaded onto GitHub all of the mappings.
No, we just
or a subset of the mappings. At least?
Subset of the mappings, yeah.
Do you have any plans to release the whole thing, or maybe the code to your tool? Because it seems like a nice primitive we can build on top of.
We plan to release the maps by the end of this month.
How about the tool?
Probably.
Maybe.
Yeah.
Probably not. All right. Thanks.
Further questions? I guess since I'm one of the authors of Explorer, I should have an opinion. So I remember that one of the things why Explorer didn't do the path sensitivity is because we wanted to go very, very deep inside the framework flows, and it become very complicated in terms of multi-threading, multi-processing if you're going to like the core of the framework, which basically means we put path sensitivity only at very pinpointed locations, apparently the wrong ones, the permission mapping. So the difference is, did you check if there could be some cases where actually a permission check comes actually deeper within the framework? Because here it seems you consider checks that come very, very early within the control flow after the entry point.
Actually, we found cases where the permission come after a clear binder following UID. Okay. And we have special way to handle those cases. So basically, we store the UIDs and then we check if they come very deep in the code. Okay.
Yeah. But you didn't go through you didn't have any problems where, like, there's this internet, I can't remember exactly what it was, where, like, message dispatching was happening between different threads within the framework, that this affected the permission mapping. You didn't see that?
We did not, no. But we have definitely some limitations if for example, if the enforcement actually happens at the native layer, then we cannot really understand if it's problematic or not.
Sure. Then I have one more question. How do you have an estimate how far the coverage of the SDK interfaces is? So this probably deals with services that are being contacted, but you have a lot of like intent-based communication and also content providers, which for instance inherit like the AppOps framework, which is responsible for enforcement. Is this something that you cover in this work?
No, we did not analyze content providers and intent. No, but we think that it should be also covered. Yeah, but the analysis should be very similar. Yeah.
If there are no further questions, then let's thank you again.